another episode of the natural number game using Lean4. Today we'll be hopefully finishing up the inequality world, starting with level 15, introducing less than. So we introduced less than or equal to previously, and we defined that less than or equal to AB means that there exists a C, which is one of my natural numbers, such that B is equal to A plus C. And we used that for a lot of different theorems here so far in the inequality world. Now we're going to have A less than B, or A less than, less than, I'm not too sure how to write less than as a symbol, but I can just copy it over. A less than B, we're going to define as A less than or equal to B and not B less than or equal to A. So yep, this kind of makes sense. Something's less than if it's less than or equal to something, and it's not equal to something. So equivalently, it's like also not B equal to A because it has to be less than or equal to B, and B is not less than or equal to A, so that means B is not equal to A. Cool. And let's prove that these. Okay, so that's the one that's in lean for less than or equal to, or less than, but a more usable one is A less than B is defined to be successor of A is less than or equal to B. This is a lot less convoluted than the first one and simpler, and then we're going to prove that these two definitions are the same. And the way we're going to do that is we're going to start by the forward case, less than auxiliary 1, A, B are both my natural numbers, and A less than or equal to B, I'm trying to copy from here, implies successor of A less than or equal to B. Actually, it might be a little neater if I move this down to here. Yes, okay. So, can we intro? Okay, nice. So we have our inductive hypothesis. So A is less than or equal to B, and not B is less than or equal to A. Okay, so we have h dot left, h dot right. Let x h dot right. Cool, and I think we have x. Yeah. So we have h dot right, h dot left, which we can access, and then we want to prove that successor of A is less than or equal to B. I'm gonna split, have h1, or I guess, yeah, h1 be h dot left, have h2 be h dot right, just to have them a little neater. Okay. And we need to prove that successor of A is less than or equal to B. So we have a hypothesis, we can do cases on it. Cases H1 with intro C H1. B equals C plus A. Nice. Can we do cases on H2? Intro C prime H2. Does that work? Oops. No, we can't turn b less than or, okay. This b less than or equal to a implies false. That's fair. So we now have b equals less than or equal to a. What if we do exists c? That makes our goal. Well, this is impossible, but that's what makes our goal that. Okay, so now we have our not b less than or equal to a. We kind of need to get that into our goal state. Okay, so let's think. So b is equal to c plus a plus c because a is less than or equal to b. Okay, so we need to prove that c is not equal to 0. Because if c is equal to 0, then b is less than or equal to a. Great, okay. So let's now do induction on c. Induction on c, or I think we should do cases on c. With 0, successor of c. Okay, we'll do the 0 case later, but for the successor of c case, let's think. Okay, b equals a plus successor of c. Okay, so exists successor of c. Or just exists c. And now we just move some stuff around between h1 to get to b. Rewrite add successor. Add h1. What's that? Add successor gets us that, and then what do we want to do? Now we want to like commute. Let's think. Let's tutorial world. Let's look at addition world. Oh, successor add. Maybe inverse. No, wait, what's that? H1, nice. Exact H1. Okay, so that solves that case. Now with this case, we have b equals a plus 0, so we can rewrite add 0 at h1. Now we can invoke like one of these. Less than or equal to equality. So I want to, we have a theorem that says if a is less than or equal to b, or is there a theorem with equality here? Let's search. Oops. Guess we can search for this. Implies, okay. Less than or equal to, no, not quite that. Less than or equal to 0. So now what I want to do is I guess we can do like the add 0 on the left side to B, or for this. We do B plus 0 equals A, flip it, and then use our definition of less than or equal to. Oops. Not that. A equal B plus C. Yeah, let's pretty much for this. Like, we want to get here, we want to get B less than or equal to A, and B is less than or equal to A if B plus something equals A. So we can add 0. We can do add 0 B. Now B plus 0 equals A. And now how do we turn something into like a less than or equal? Can we just do like B, let's see, H3 be defined as B less than or equal to A. Does this work? No. That's not quite right. We need to apply our definition using this. There is the C. Did I use this in here? Okay, so we have this. We go with this. Okay, so we start here because it's 1. Okay. So back to here. It's just 0. B equals successor of A plus 0. So we have B equals A. Okay, wait. We actually don't need this part. Exists 0. Can we have like... No, we need to like use the B less than or equal to A somehow. Because we need like the absurd thing. Let's look at our advanced proposition world, where you do stuff with false, contradiction. Oops. I need to think about this. After a bit of refresher and look over the tactics and techniques available to myself, I figured out that here we don't really care about the goal. We just can already prove that this is false from our hypotheses. So we could just apply false.elim, and then it says from a false, any desired proposition C holds. So this is just X false. So here we want to prove our hypothesis false, and now we can just apply H2 to have b less than or equal to a is what we want to prove. And if we can prove b less than or equal to a, then we reach a contradiction. And how to do this? Well, we just say exists 0, rewrite add 0. Let's see. Let's do this at h1. Rewrite h1. Refl. Cool. Because a equals a plus 0. And that solves our case for less than auxiliary 1. And now let's prove the other way. Now we want to prove lemma less than auxiliary 2. Let's just copy over this, and we'll swap the ordering of the two expressions. That's intro H. Now we're starting with our hypothesis is a less than or equal to b, and I want to prove a less than or equal to b or not b less than or equal to a. So we want to prove both of those from this. So we're probably gonna have like an and.intro. Is this what it's called? And.intro. Yes, and then here we're gonna need to have this should be a proof a less than or equal to b, and this should be a proof of not b less than or equal to a. Okay. So successor of a less than or equal to b implies that a less than or equal to b. I think that's one of our theorems. We're going to chain two theorems with transitivity. So here we want to get a less than or equal to b if a plus 1 is less than or equal to b. Is that really not one of our... Okay, so we have, oh, a less than or equal to b implies a is less than or equal to successor of b. We don't necessarily want that. I guess we can chain this and transitivity. So we can have, we can call this h1, h2, be defined by less than or equal to successor self a. Okay. Now we could have h3 be defined less than or equal to transitive. So you provide an A, a B, and a C. So a successor of a b. And this should be h3. We want a is less than successor of a, and successor of a is less than b. Okay, so now I want to provide h2, and now I want to provide h1. Cool. And now we have h3, which is a less than or equal to b. Nice. And then we want not b is less than or equal to a from our h1. How do we do this? So we have the right side of this. So can we just like, how to deal with ands? Can we do like a left and right? What's our way with ands? Let's look at our advanced proposition world. Okay, so we can call constructor. Nice. So let's call constructor exact h3. Okay, now we want to improve not b less than or equal to a. Now we have a not in our goal state. What do we do then? We have a not in our goal state. We had a not in our goal state before. Let's look at our regular proposition world. Rewrite not. What do we do here? Went from this to this. No, it's not quite what we want. Maybe in our advanced addition world we had something. Okay, so here's our goal was a not equals. Then our goal became false. Why did our goal become false? Because we intro h. What is h? Okay, so I think if we intro, then we can make our goal false. Intro, I don't know, h4. Nice, okay. A less than or equal to b. Okay, so let's think here. So we want to prove false. And we have successor of a is less than or equal to b, and we have b is less than or equal to a. This is progress. So I think we don't really care about h1 and h2. I think I can also just do comment these out, just because it's kind of getting in the way. Where h2 is this. Okay. Let's call this h2. Successor of a is less than or equal to b, and b is less than or equal to a. Let's look at what we have. Not successor itself, that's fine. So we have one or the other, a less than or equal to b, or b less than or equal to a, not both. Well, no, we can't have both. Let's equal to transitive, let's equal to successor, let's equal to reflexive. None of these seem to be helpful. Not successor of a is less than a. That seems promising. Well, let's start by just doing our cases. Cases h1 with intro ch1, intro, okay, let's see, cases h2 with intro dh2. Okay, what are we left with here? So we have a equals b plus d, b equals successor of a plus c, should we do cases on C and on D and then get into weird things? Maybe? Is there an easier way? Oh, well, here's this. Okay, rewrite h1 at h2. So now we have a equals successor of a plus c plus d. This seems promising. Let's look at our advanced addition world. Oh yeah, here it is. N is not equal to successor of n. Okay, we can like left cancel the a to get 0 on both sides. I think that's the way to do it. So a plus b equals a implies b equals 0. Okay, I think we want to left cancel everything until we're just left with 0 on the sides. Okay, I think that's what we do. We can apply like 0 not equal to successor or something like that. What's it called? Yeah, 0 not equal to successor. A. So our goal is to have 0 is equal to successor of a. Okay, and now at h2 we can do some moving around. Rewrite at h2. What do we want to do? Add successor. Is that what it is? No. Well, kind of. I want to get the a out of there. Successor add. Okay. Add com. Okay. Successor add. Cool. Add commutative. No, this add commutative was not quite what we wanted. Add commutative, successor add a plus b, that's fine. Commutative c, can we do this? Or, sorry, that should be a. Cool, okay, and now add like left cancel, whatever it's called. T plus a. Oh, I guess we want to do add 0. A. Nice. And now we can do add left cancel. T A B. Okay, we need to move the parentheses around, so it should be a plus something. Now we need to move the parentheses around here because now it's a plus 0 plus successor. So is that like add associative? Add associative. Add left cancel. Yeah, left cancel. Okay, so this needs to take a TAB. So the T would be A. T plus A. Does this work? Okay, so T Okay, T. Yeah, let's just stop it here. This is getting kind of long. Oops. Okay. Rewrite at h2, no comma. Okay, so this is saying we need T A B. So our T no, we don't rewrite, we just use it. Have, I don't know, H3 be defined as add, left, cancel, this, H2. What is our H3? 0 equals 0 plus successor plus D. Huge. Rewrite at H3 at 0 add successor. Add. Okay, and then now we have we want to use our not equal. Successor not equal to 0. I guess we could do equal dot symmetric to flip them around. Have H3. Okay. Now we can apply almost there. Successor not equal 0. H4 0. C plus D. Or I guess instead of having B successor of A, we can successor of C plus D. C plus D. Exact H3. Let's go. Okay, so this proves less than or equal to auxiliary 2. And that solves inequality world 16. And finally, okay, level 17, the definition of less than. So we're going to have just copy this. We could just add this. I'll just copy this over. Definition less than AB minat. We'll define it as what we did before. Oops. Then we're gonna have instance less than and then we're gonna have left lemma this. Okay. A, B are naturals. I think I can actually move this into less than or equal to dot lean. A, B are naturals. A less A LT less than less than. I'm not sure how to write that with Unicode. I'm just gonna copy it over. A less than B if and only if the successor of A is less than or equal to B, and we'll define that by the things we just did. constructor intro A, let's see, A, B, oh no, intro H. Why is this not happy? Oh, anything I need to reload you. Restart server. Cause I just copied the constructor for less than the other file, so it needs to like reload to like load it in. Then once it loads it in, it should be happy. Reload window. Let's see if this works. Don't want an update. We want lean. That's going to reload all the lines. And let's see if this works. Okay, nice. Intro H. And now we can apply exact. See, this should take A, B, H. Nice. And then intro H again. Exact LT aux2 ABH. Spelled aux wrong for auxiliary. Okay, I think I can actually do this with. Oops. There might be a way to like code golf this to do like something like. LTX1, LTX2. Does this work? A, B, A, B. Nice. And then since we're using exact here, I think we just do this without the by maybe. Does this work? Not sure if this will work. Yep, that'll work. Okay, so this is the same thing as the other way. We just prove it like this with the anonymous constructor, and we just provide both definitions. Great, and that solves the inequality world. Thank you so much for sticking around and watching all these videos. I had a lot of fun making them. Please leave any comments of what you want to see me do next, and yeah, hope you learned some Lean 4. I sure did, working and struggling through all these things and learning all these helpful tactics. It was fun porting Lean 3 to Lean 4 and working through the natural number game and porting it over. And I'm glad to see that we were able to solve all the problems in the natural number game without too much difficulty. It was definitely hard, but we were able to do it in the end. Alright, thanks for watching.